That TCP SYNAC defense is based on the idea of making sure that the client does some work before the server does some work. From the attacker's perspective, the problem with making requests in general is that you have to deal with the server's answer. And so if you flood a server with requests over its network, it can flood your network back with the answers that it provides. A way around that, though, is to get other people to do the asking or to deal with the responses. Spoofing means sending a message using someone else as the from for a message that you write. Spoofing can refer to email addresses or IP addresses at the network layer, and so on. And it's not always inherently bad. Sometimes people working at a company respond as if they are a part of the company as opposed to from their own account, and that kind of spoofing is okay, but spoofing can also be used maliciously, especially for denial of service attacks. DNS gives an attacker leverage right from the start, because when a client sends a DNS request, the server is going to answer that with an answer that is bigger than the request. It always includes the question in addition to its answer. Furthermore, if the client requests recursive resolution of an address, then it can create a lot more work on the server than it created for itself. But spoofing leverages this further by having a single client send multiple packets where it identifies the source not as itself, but as somebody else. That way, when the server sends all of its responses out, it is sending them out to the network to different destinations, like machines A, B, and C here, which might be arranged to be far away from the requesting machine, so that they're not coming back to this machine or even its local network clogging up this machine's network. And if the attacker is able to continue streaming these spoofed packets in different places, its network load will stay low, while the network everywhere else will be occupied with these responses. The DNS server is unlikely to be able to deal with this very much, because as far as it can tell, it's getting legitimate packets that have legitimate destinations with legitimate queries in it, and so it can't distinguish that from other queries that it does want to answer. In this picture, though, you can see that when this laptop is sending requests with spoofed IP addresses that are not even on its network, then this router here could notice that. And so a possible solution that is in place at many layers is for this router to detect that the source indicated on the packets it's receiving from some direction don't make any sense, they must be spoofed, and so they can be dropped. This creates new work for the router, and this is one reason a router might not want to do this, because it would have to look at the source part as well as the destination part of a packet. It would have to be aware of larger amounts of the network topology to make sure that it makes no sense for a packet to come from that direction. Still, it's one of the best defenses in place for spoofing-based denial of service attacks. These checks particularly tend to be in place for DNS, since DNS is often used for this kind of attack. But it's not just DNS. The same idea works for any kind of database where you can send a query and redirect the response based on a spoofed IP address. That includes memcached, where the answer from memcached can be much larger than the query that is sent. That is, by a much larger factor than a DNS response compared to a DNS query. In 2018, GitHub was attacked in this way, where attackers sent a bunch of small requests to many different memcached servers, but asked each of them to send their answers to GitHub. So GitHub was suddenly flooded by a lot of information that it didn't ask for. In fact, for about 15 minutes, 1.3 terabytes of data were sent to GitHub per second. And that was enough to take even a large, well-structured GitHub system down for a while. This was pretty hard for GitHub to deal with, and the source of the problem really was not their security, but all of these memcached servers that should not have been publicly accessible. But because they were publicly accessible, questions could be sent to them, they could be tricked into sending answers, and they could be tricked to sending it to the wrong place. So globally, the kind of solution to this attack is to not have those servers publicly available.